Hola, coming to you live from Oakview Middle School. Hi. So I hope you liked my little Halloween video. It was fun to make. I hope you enjoyed it and had a very happy Halloween. But now we got to get back to business, right? So our next video is talking about Earth's history. And really, the question that we have to answer is, how can we find out about Earth's history, right? About Earth's past? What evidence do we have that that Earth is 4.6 billion years old, if that's what you choose to believe, right? There is some evidence that helps support that, okay? And one of those pieces of evidence you talked about last year and you've heard of for a long time, these things called fossils, okay? So, right, fossils are trace from the past, okay? The oldest known organisms that we think thought to have lived 3.5 billion years ago and were found in Australia, right? So we're thinking, based on lots of different scientific research, that these organisms that were found in Australia are 3.5 billion years old, okay? The oldest organisms that we know of. Geologic process that occurs today happened in the past. So what this means is that our Earth right now is changing, right? It's changing and changing and changing and changing and changing. That tells us that it's probably happened since Earth has been formed. Earth has been changing. The surface has been eroding and weathering, and new rock has been formed, and so on and so forth. That's called uniformitarianism. Okay? This idea that what has happened is what's happening now probably has happened in the past. So these geologic processes happen over and over and over and over. Rates of these processes change and vary over time, right? There might be some times in history where lots of new rock is formed, lots of volcanic activity, so on and so forth. And then there might be other times where there's very little volcanic activity or little rock is formed. So and then likewise, weathering and erosion. There might be times in Earth's history where lots of weathering and erosion occurred, and then there might be times where very little occurs. Layers in the rock. So if I look at a rock, the layers are called strata, and they can show you sequence of events. The events on the bottom happen first. The events on the top happen last. The fact that one layer of rock is older than the other is called relative age. We talked about that. Igneous, metamorphic, and sedimentary rock all have layers, and I can look at those layers and kind of get a timeline of when that rock was formed. Okay? The law of superposition. We've talked about it, right? The law of superposition says older rocks are below younger rocks. Younger rocks are above older rocks, right? If those layers are not disturbed. Think of the relative age. We still don't know how old the rocks are, just that their age compares to the rocks around them, right? So if I have layers of rock, I know that layer 1 has to be the oldest if it's undisturbed. Layer 1 had to be there before layer 4, right? Common sense. That the gravity draws everything down. So I couldn't have layer 4 and then 3, 2, and 1 fill in after that. No. It has to be layer 1, and then layer 2, and then layer 3, and then layer 4. Okay? So that's a law of superposition. Movement of Earth's crust can cause these rock layers to change position and affect the calculation of relative age. So, right, these layers are laid down, then, right, movement in the Earth's crust, causes my layers to maybe get pushed up or heaved, right? Well, now those layers are disturbed, and I don't know specifically, did this layer get put down first, or maybe this happens, right? Now I have no clue. It looks like this layer was laid down first. So movement in the Earth's crust can cause these layers to be disturbed, and then the law of superposition can't go in effect because the layers have been disturbed. Okay? Absolute dating. So we talked about relative dating. This one has to be older than this one, but I don't know how old they are. I just know that this one's older and this one's younger. Absolute dating, which is called radiometric dating. Okay, radiometric dating compares parent and daughter isotopes within a rock material to tell the exact age. Now, an isotope is basically, you don't need to know what the definition of an isotope is, but Radiometric dating takes an unstable nuclei, and as it breaks down into a daughter isotope or a daughter particle. So it starts as a parent particle, and it's very unstable. Over time, it breaks down into a daughter material, which is a bit more stable. Okay, so radiometric dating, right, takes this parent material, and over time that parent material breaks down into a daughter material. The reason we use that is because the breakdown is very, very calculated. I'm able to, regardless of its environment, whether it's underwater, up in the air, or buried in ground, it will decay or break down at a very constant rate. So based on how much parent material and how much daughter material there is, I can calculate how old that organism is to a certain degree. Right? Elements that work within this method of aging include carbon, potassium, uranium, thorium, and rubidium. All of those elements break down over time. They break down from a parent material to a daughter material. Okay? These need to be present in order for the rock to be dated within this method. Okay? This picture, which is a picture from your book, shows you in the red, right? Something dies, and let's say it has potassium in it. That potassium breaks down at a systematic or calculated manner over time. So I start with 100% parent material. Now, I can calculate how much time is it going to take for that half of the parent material to turn into daughter material, which is the blue. This time frame, how long it took it from go to 100 parent to 50% parent, is called its half-life, the organism's half-life. Okay? And then I can then calculate how long is it going to take for us to get this part to become half again, right? So I'm starting with 8 red circles, and I end with 4 red circles. So that's another half-life. The time it took to get to here is the same time it's going to take to get to here. Right? So let's say, for example, it takes 4,000 years for half of the parent material to turn into daughter material. So that means that this is going to be 4,000 years. That also means that this is going to be 4,000 years, because I'm starting with 8 circles at this point. It's going to take me 4,000 years to get down to 4 circles. And then it's going to take me 4,000 years to get from 4 to 2. And then it's going to take me 4,000 years to get from 2 to 1. Right? So for example, I start with this material. Okay? That's 100%. That's all red circles. Now I've got half left. The time it took me to go from all red to half red, that's its half-life. And then now I've got this much left. How long did it take me to do that? That's its half-life. And then now I've got this much left. That's its half-life again. And now I've got this much left. A half-life. This much left. A half-life. This much left. A half-life. Right? So each time I rip that piece of paper, that's a half-life. I'm calculating how much time it takes to get from all parent material to half parent material. Right? Whole sheet to half sheet. 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 Now, over time, I'm going to get to too small of a parent material to calculate. So absolute dating only lasts for a very short period of time in comparison to Earth's history. Okay? So I can only use absolute dating for a period of time. Once I get so little parent material left, then I can't absolute date something. That does it for our Chapter 8 notes, talking about fossils, talking about absolute dating, talking about relative dating. All right? I hope you wrote down some questions. We'll talk about them tomorrow or whenever this is due. All right? Peace out, homies. Before we get there, let's take a look. Okay? So, fossils are dead remains, right? Remains of animals or plants that lived a very long time ago. Now, they went through... Not everything that has ever lived or died is fossilized. It has to go through a certain process. It has to be buried in a certain area with certain conditions to really have the opportunity to fossilize. Most things that die are broken down into their components and re-released into the geosphere. The energy, all of that stuff is broken down and re-released. It takes a very specific thing or series of things to happen to an organism in order for it to become a fossil. Okay, but we can use those things, right, to find the relative and absolute age of rocks. Okay, now last week we talked about the relative age, right? If I have an organism down here in a layer of rock and I have an organism up here, which one's older? The one on the bottom has to be older because of the law of superposition, right? This layer had to be laid down before this layer came about. Okay? And then absolute age, we'll look at that in a little bit. But we can use fossils in two different ways, right? To relatively age things, this lived before this, and to absolutely age things. This lived X amount of years ago, 300 million years ago, or 65 million years ago, whatever the case may be. We can use those fossils to absolutely age, get a very good estimate of where or when that organism lived. Okay? Fossils give us clues about the past and geological environmental changes. So I can look at fossils and maybe identify what kind of environment did that organism live in. Was it an oxygen-rich environment? Was it a desert type environment? Was it a rainforest type environment? What was the atmosphere like during that time that organism lived? So I can look at environmental and geologic changes as well. Okay? Fossilization occurs in many ways, but there are many types of fossils. Okay? So there's a picture, right, of a famous organism, okay, a dinosaur or multiple dinosaurs, and those are kind of some of the coolest, biggest fossils that we've ever found. But there are a lot of other organisms that go through fossilization as well. And this is just one type of fossil. There are multiple types that we're going to talk about. Okay? So, if we talk about what types of fossils, there are mummifications. Right? Maybe not those mummies, but there are, right? That's a type of fossilization process, mummification. Right? And then there are organisms that are trapped in amber, okay? And then there are tar seeps, or these tar pits, that can fossilize organisms as well. Freezing, you might not think of that as a fossil, but it absolutely is. So if an organism got trapped in water or a slushy mixture, and that mixture froze before that organism could start to decompose, then that organism is preserved until that ice melts. Okay? And then we have petrification, right? In petrification, usually we see that with wood. You have petrified wood where mineral replaces the wood fibers, the organic material, and minerals replace those and harden, and then what's left over is something that looks like wood, but it is a rock, and that's petrified wood. So I'm not going to have you write one or two sentences down, but what I do want to bring to light is kind of some of these the reasons that these fossils are different, right? So mummification typically happens in dry locations. We wouldn't see a lot of moisture where mummification occurs because when an organism mummifies or is mummified, basically all of the moisture is taken out of the organism before it can start to decompose. If there's no moisture, then decomposition has a hard time happening. Now, it may happen, but at a very, very, very slow speed. Okay? So typically mummification happens in dry locations. Amber, usually from like tree sap. Okay? So amber is basically hardened tree sap. So am I going to find an elephant encased in amber? Probably not. And why? Because it's tree sap, right? There would have to be a massive amount of tree sap to engulf an elephant. So what kind of organisms do you think that we typically find in amber? Right. Small insects, small organisms, things that can be easily, trapped. They land on a branch of a tree, and then that sap is dripping down that tree, and it encases it, and then that tree sap then starts to harden and gets buried before it can be broken down, and that turns into amber, and then within that is the organism that is safe from decomposition. And then we've got tar seeps. Tar seeps or these tar pits are petroleum oozes to the Earth's surface. So there are some places. There's a place out in California where this petroleum, right, or oil, oozes to the Earth's surface. Now, if I'm an organism and I'm walking by this tar pit, somebody pushes me in or I fall in, right? That's pretty warm stuff, right? Because it's coming from the interior, inside of Earth. So I'm probably not going to get out, and then I sink to the bottom, and that stops the decomposition process, right? I die, but the microorganisms are not able to decompose or break down my body. So then I am preserved until either the tar seep, the tar pit dries up, or the tar gets extruded, or whatever the case may be. That organism then is brought to the surface, and then we can look at that organism as a fossil. Okay? And then frozen, right? We talked about that. Frozen soil protects animals. So if I am a plant in the tundra and the tundra does not thaw, then decomposition can't occur. That's why we have freezers. That's why we put meat in the freezer, or organic material in the freezer, so it doesn't break down, so it doesn't spoil, so to speak. Right? That's why we have freezers. So in nature, if I have an organism that has always been frozen until it thaws, that organism is going to be preserved from decomposition, and then I'm going to be able to look at that organism and kind of study it. What environment did it come from? When did it live? So on and so forth. And then the last one is, right, petrification. Groundwater within the minerals replace the animal or plant. Like I said, typically this happens with wood, and it's this groundwater that's bringing minerals in, that's decomposing that that organism, and then the minerals that are in the water replace the wood, and you're left with this rock that looks like a piece of wood, or this piece of wood that is rock instead of wood material. Okay? Some of these pictures, right? So this picture is a picture of amber, and then encased in it is an insect, right? Maybe a mosquito or maybe a fly, something like that. And then that mosquito or fly is preserved from decomposition because of the amber. Okay? And then we've got mummification, right? Dry location. So a lot of the times, right, you think of mummies, we think of we think of humans that have been mummified years ago in the Egyptian era, whatnot. But that's not always the case. There are in some instances where organisms can be mummified, so to speak, in these very dry, desert-like environments. And then, right, a lot of mammoths, right, the woolly mammoths that lived in the cold environments, some of them may have been encased and died because of these harsh conditions, these very cold conditions. They could have died on the ground, froze solid, and then got buried over with snow, and that snow then eventually turned to ice, and that ice encases that woolly mammoth until the ice thaws. A paleontologist or an archaeologist or a geologist comes across it and exhumes it, and then we can study that organism, right? So that's encased in ice. And then this is just a picture, and you probably can see it better in your book, but that's a picture of petrified wood. It looks like a piece of wood, but it actually is minerals that have hardened into rock. Okay? So this is kind of the actual organism that is fossilized. But that's not the only type of fossils that we find, right? It's not just organisms that are fossilized, whether that's plants or animals. There are other types of fossils that we see. Okay? We could see imprints, molds or casts, coprolites, or gastroliths. Okay? What are all those? Well, they aren't organisms, right? They're not the organism that has died and then been fossilized by those different processes. But this is evidence that these organisms lived. So an imprint into something that was fossilized, okay? It displays on the surface features. So for example, a leaf that falls into an area that on a rock or on a layer of sediment that then becomes hardened into sedimentary rock, well, we can peel back those layers and boom, on the surface of that rock or on the surface of that sedimentary rock, we can see this imprint of a leaf. And based on where that layer is in the sediment, we can gauge of how old that organism is. So we've got imprints. Okay? And then we've got molds and casts, right? So this is empty spaces filled within. So here is an example of a mold and a cast, right? So this was a rock that was broken apart, and inside you've got this fossil. You've got a cast, and then you've got a mold, right? When you break that apart. The mold is kind of what fills the open area, and then the cast is the void in the rock. Okay, so you've got molds and casts that can show you organisms. And then you have coprolites. You're going to like this. It's poop. Poop, right? So an organism lived, right? A dinosaur poops in the woods, and then that poop then becomes fossilized through a different period, through different processes. Maybe it poops in the shallow part of where a river deposits a lot of sediment, and then that poop then gets covered with sediment, pushed down, and made into a fossil, right? I can look at that and I can see, right, that this is not dung, it's not poop anymore, it's minerals, it's rock, but it fossilized the remains. It fossilized that remains. And then the last thing is stomach stones, which is gastroliths. Okay, so these different things. Now, the reason that I show you gastrolith, right? How do I know, if I look at that stone, I come across that stone, how do I know that that's from a stomach of an organism? Well, there's evidence in history that these different organisms had rocks or stones in their intestinal stomachs and their intestines that helped churn the food over, break it down. So over time, you would eventually expect to see that any sharp edges from the stones were rounded off, right? And okay. A mark left behind an animal gives clues to the past. These clues are called trace fossils. So everything we've looked at so far is actual evidence of the organism, whether it's poop or an imprint or a cast and a mold, or it's the actual organism that's mummified or frozen or petrified, whatever that case may be. But if I'm an organism and I'm a dinosaur and I lived 65 million years ago, I may walk through a mucky, muddy environment, and then that mucky mud gets the sediment fills in those areas, and then that gets pushed down and solidifies into sedimentary rock. And then over time, it comes to the surface, and I can look at that and say, oh, there's an imprint, right? There's an imprint of an organism that stepped into this mucky mud before it was fossilized. And that's called a trace fossil, right? And this can include tracks, which is what we just talked about. Footprints, borings, right? Burrowing into a hole, burrowing into the side of a tree, burrowing into, plant life, animal life, so on and so forth. And then burrows as well, right? So these kind of boring into a tree or burrowing, right? So if I'm a rabbit, so to speak, I make a burrow, right? I dig into the ground, and that becomes my house, so to speak. So that's a burrow. Right? This helps us learn about animals' habits, okay? And these habits we can study because we can see, wow, these things that lived 65 million years ago, right? These dinosaurs that lived 65 million years ago, what did they look like? How did they act? What was their foot span, right? From one foot, from the left foot to the right foot. That gives you kind of a gauge of how tall that organism is, right? And then, so if I've got in this fossil site, I've got a set of tracks coming in this way, and then I've got a different set of tracks coming in over here, and then we see there's an indentation right here. Something got pushed down, something happened there. And then I see these footprints. Are they big? And I also see drag line with that organism. What might that actually tell us as scientists? Okay, I'm looking at this site, and these are all fossilized footprints, so to speak. Right? So I've got a small organism. I can tell that it's small because it's got small footprints. I've got large organism because I can see big footprints, and they're further spread apart than these. They come together. They meet at some point. Something happens. What do you think might happen? Death. Right? Based on what then I see here is I see the big footprints moving, and I see that they are moving in this direction. Right? This is moving in this direction, this is moving in that direction. And then I see this big footprints moving away, and I also see these marks, these drag lines. So what might this be? That might be the organism maybe died and is being dragged away. Okay? The animals that left an index fossil must meet the following oh, no, we're not there yet. Right here. So we've talked about index fossils, right? So a fossil that only occurs within a rock layer of a certain age can be used as an index fossil, right? An index fossil is very crucial and key to Earth's history, to geologic time scale. Okay? Now, the reason for that is because there are 4 things that an index fossil has to satisfy in order for it to be an index fossil. Not every fossil is an index fossil, right? They have to only have lived for a short period of time. They lived over a great area, so they're found on multiple continents or multiple countries. Okay? They must be different than other fossils, so unique, easy to identify, and then they must have occurred within a lot within the rock layers. So pretty common, right? I come across them a lot. It can't just be one tiny little fossil. There has to be lots of them within that rock layer. Okay? And that helps us determine the age at which these organisms lived, because I can then date this index fossil back to a certain age, and I can say, okay, any rock layer that has this fossil in it, I know that that rock layer is 300 million years old, or 65 million years old, or 1 billion years old, whatever the case may be. However old scientists determine that index fossil to be, then I know that the rock layer in it is that old as well. So anywhere in the world that I come across that layer of rock, I know that that layer of rock is that age. And then I know that layers below it are older and layers above it are younger. Okay? All of this allows rock layers that can contain particular index fossils to be dated accurately, and that's what we just talked about.
That does it. I hope you liked it. We'll see you tomorrow. Peace out, homie.